Good morning, everyone. I want to welcome you to the Claude Hocott Lectureship in Petroleum Engineering. We are pleased to have Dr. Eric Cayeux of the Norse Drilling and Well Modeling Research Center, Norwegian Research Center, to talk to us this morning. And Eric has been at Norse for 16 years, and prior to that, he spent 18 years in industry. So he has a wealth of experience and expertise working in software solutions in drilling. He's the software architect of drilling and automation, diagnostic solutions at Norse, and has developed several mathematical models that are compatible with real-time constraints, which I think he'll be talking to us about today. He has a PhD in petroleum engineering from the University of Stavanger and master's degrees in civil engineering and software engineering from universities in France. And without any further ado, I'm going to pass it off to Eric and virtually welcome to Austin.
Thank you very much. So let me share my screen and hopefully, yes. So I hope you can see the screen now. Good. So good morning, everybody. So the topic of my talk today is about the estimation of the internal state of the drilling system and its application for drilling monitoring, drilling automation, and autonomous drilling. So my name is Eric Cayeux, and I'm Chief Scientist at Norse. So the outline of my presentation is the following. So I will start with an introduction and motivation for the work that I will be presenting today. And then I will go into the details of the modeling of the drilling process, and then look at how this can be used for early detection of the deterioration of downhole conditions. And then also how these different real-time models can be used also for automatic drilling assistance. And the last thing that we have been working here at Norse about completely autonomous drilling. I'll just give a kind of appetizer on this topic there, and then I will take some conclusion. So about the introduction and the motivation. So as you know, the well construction process is a cycle where we start with selecting the target, defining the architecture for the well and the trajectory, and then utilizing this information to do some drilling engineering calculations. And then we go on with planning the operations to make that as safely as possible. And then we really build the well by the drilling operation. And then we capture the information which has been recorded during the drilling operation to do some post-analysis, which is a new input for the next cycle for planning the next well. So the topic of my talk will be focusing on the drilling operation itself, and therefore it will be very much focused on real time, as it is a very important aspect for solving those problems during drilling operations. Now, real time means that actually we are confronted with quite challenging problems during drilling operations, especially the presence of very long and strong transient effects. Here to illustrate this, we have a picture of the actual drilling operation of a extended reach drilling well in the North Sea, where we are reaming down to get to the section TD, or to the start of the 6.5 section, drilling section. And we can see that when we are reaming down, so the pump pressure does not stabilize before 7 minutes after the mud pumps has been actually started. And actually it's almost coinciding with the end of the reaming down of the operation. So you can say that within the whole reaming down part of this stand, there is no places at all where we have any steady state conditions. And this is quite common actually, that we have so much strong transient effects that steady state condition doesn't exist. Now, if we use standard steady state models like the one which are used in drilling engineering, so we are far from being able to reproduce what is observed. So this schematic is showing actually the execution of a friction test where we are first rotating the stress ring and having some torque, and then we are stopping the rotation, and then we are doing lift up and then a slack off. And we can see that on the torque, when we stop the rotation, the torque doesn't return back to zero. It's only when we are actually lifting up and slacking off that the torque is diminishing slowly with time or with the depths. Similarly, so the hook load is not increasing immediately to the pickup weight and is not decreasing immediately to the slack of weight, while actually those steady state models that we are using in engineering are predicting that actually the torque goes directly to zero when we stop the rotation, and the pickup weight and the slack of weight are reached immediately as soon as we change the direction of movement. So there is a lot of discrepancies there which are not sufficient for dealing with real-time operations. And during drilling operations, so of course we are facing drilling incidents. Drilling incidents can cause delays, and we need to make sure that we have drilling operations which are as safe as possible. Here is an example of an actual drilling operation in the North Sea where we have fracturing of the formation. As you can see here, just before 5:20 p.m. So everything was very steady flow rate, very steady bomb pressure. And the flow rate out was also very steady on the flow paddle. And then suddenly it started actually to decrease, indicating that we have fractured the formation and we are starting to lose mud to the formation. So these kind of things needs to be captured as quickly as possible and to be avoided if possible. And then the next thing, which is quite important, is since the drilling operations are conducted by human beings, and human beings are very creative, so you can see how friction tests are executed by a team of 2 drillers. So actually we are talking not about many different drillers, we are talking about 2 drillers. And through this sequence of different friction tests, you can see the variations of those friction tests, how they are executed. Some of them are far too short, some of them are far too long. They are not consistent, and it's much more difficult actually to interpret the information which has captured after those friction tests. So consistency is also a problem when everything is driven by human beings. So the research question that we have been addressing for some time now is it possible to create mathematical models of the drilling process that can run in real time and which match actual measurements, even though the conditions are extremely unsteady? Here I have an example of an operation which is performed on a floater in the North Sea. It's not very much heave that we have at the moment for this drilling operation. It's plus minus 1 meter. Yet we can see that the hook load that is measured when we are lifting up the string of bottom is ranging between 60 metric tons and up to, at the end of the lifting, up to almost 120 tons. So it's 60 metric tons of difference between the start and the end. And you see those oscillations which are corresponding to the heave movement that we have on the rig. And as you can see here with models, so we do manage to reproduce quite well actually the observations. And we also can see how the torque is decreasing while we are lifting up after we have stopped the rotation. And this also can be reproduced quite easily. The green curve being the model one compared to the blue one, which is the one which is recorded in practice. We want also to be able to utilize real-time information to predict whether there is something abnormal coming into the well. Here is an actual operation. I will come back to that operation later in the presentation, where we could see actually that the cuttings transport was not performing at all as it was expected. We had actually almost no cuttings coming to the surface. And of course, when the drilling operation continued to drill for several stands without having any cuttings coming to the surface. So there was quite likely that some disaster would come, and they did arrive. And finally, so we can try to utilize those type of models to have much better consistency in the operation. And this is actually friction tests which are executed by an automatic function. I will mention that at the end of the presentation. And as you can see, those friction tests are extremely consistent. But you can also notice that those friction tests are getting longer and longer when we are getting deeper and deeper into the well, to account for the fact that actually the drill string is more and more elastic, and that we need more time actually to get the bit movement at the bottom when we are doing the lift up and stack of sequences. So that's the motivation. We want to have models which are real-time compatible, which can help actually improving the performance and the safety of drilling operations. So how do we do those kind of models? So basically, the first thing we need to notice is that actually we have a system which is real life system, and we want to make those different processes that simulate this the system itself. These models needs to get exactly the same inputs as the actual real life operation. So we need to get what is the top of string actual velocity. We need to get what is the top of string rotational velocity, the flow rating, and so forth. That's the inputs, the boundary conditions that we have. And then this model will produce outputs. And at some stage, we will see that we want to compare those model outputs with the actual system outputs that we have there. Now, one first thing that needs to be considered is the fact that we are pumping fluids into the system for both transporting the cuttings, cooling down the BHA and the bit, and so on and so forth. And therefore, there is actually an important aspect of the process, which is actually heat transfer. So basically, what we can see here is some results of the simulation that we have done with after a certain period of circulation about the temperature inside the string and the temperature into the annulus of the fluid at different depths for a well which is quite long. It's more than 8 kilometers long. The red curve here is the geothermal gradient. It's quite high temperature for this particular well, so we're reaching well 100 degrees Celsius at the end, and we see how the temperature is also penetrating into the formation rock in this second abscess that we have there. The color coding is that if it's blue, it's cooler than geothermal. If it's red, it is warmer than geothermal. Now, if we look at the process itself, it's actually a dynamic one. And as you can see here, we see that how the temperature is evolving inside the string and inside the annulus when we start from geothermal conditions. And the differences that we get there for the temperature along the string and along the annulus is simply due to the fact that we have advection, that we have movement of fluid inside the string and the annulus, that we are generating heat through pressure losses, both inside the string and inside the annulus, and we are also producing heat through friction, mechanical friction, because of the rotation of the pipe inside the deviated well. And these all things are actually generating this heat transfer that I'm simulating here, which is shown at a speed up of 200 times compared to real life. So we see that actually we cannot do drilling heat transfer calculation without considering drilling hydraulics, without considering drill string mechanics. Now, the characteristics of the fluid are actually dependent on many different things. Drilling fluids are a mix of different components, both solid, liquids, and sometimes gaseous. And because of that, actually, the heat transfer calculations are depending on what is the actual mass density of the fluid and the specific heat capacity and thermal conductivity of the fluid. Now, those characteristics are both dependent on the composition, and they are also dependent on the local condition of pressure and temperature. So we can see here for the mass density how the PVT behavior is changing as a function of pressure and temperature, and also on the content of cuttings. We can see also here how the specific heat capacity, CP, is changing as a function of temperature and also on the presence of cuttings, and the same for the thermal conductivity. So these will have influence on the heat transfer calculations. So I can illustrate that with this animation, as you can see here, where we have actually a simulation where we are producing cuttings, which are shown here. And this production of cuttings are changing both the mass density of the fluid, which is circulated inside the annulus, but it's also changing the specific heat capacity and the thermal conductivity, as you can see here on those two traces there. And therefore will influence the actual temperature evolution while we are simulating this operation. So material transport is also an important aspect. So to do this drilling heat transfer calculation, so we need to consider the side effects of free-over type of mechanisms, both hydraulic mechanics and material transport. Now, this being said, there is a reverse action. So if we look at the rheological behavior of drilling fluids, it depends on both pressure and temperature, as it is shown here from measurements made with a scientific rheometer, an Anton pyrheometer, and the range of pressure and temperature between 25 degrees and 75 degrees Celsius, and between atmospheric pressure and 200 bar. As you can see, it changed quite a lot. And also it depends on the concentration of solids. So if we are transporting solid particles like cuttings, so the rheological behavior is also changing as well. So this is reflected through this simulation there, where we can see how temperature and transport of cuttings is actually changing the rheological behavior of the fluid. The rheological behavior of the fluid is shown inside the string and inside the annulus. So this is the string trace and this is the annulus trace. And these rainbow colors are associated with the fan 35 rheometer speed. So the blue one are for the low RPM, and the red one is for the high RPM of the fan rheometer. And you can see for the same fluid being transported there, because it's exposed at different pressure and temperature conditions, and because it has also a certain concentration of cuttings, the rheological behavior is not the same along the well. So there is a mutual interaction between heat transfer and material transport and the hydraulic side. Now, cuttings transport is a very complex problem. When you look at what happens to a cuttings particle, which is exposed to a three-dimensional fluid velocity field, it is exposed to many different forces. Of course, gravitation, buoyancy force, but also viscous drag, lifting forces, and torque, which is making the particle spinning, because the particle is never spherical. It's always aspherical. And if you consider the fact that this velocity field in the cross-section is quite complex because of the pipe rotation, because of the actual movement of the pipe, and because of the fluid velocity itself, or the flow rate, the bulk velocity that we have there. So basically, this particle movement is really complicated. So what happens to those cuttings particles? Well, they can be transported directly into the high side of the borehole. If you imagine that the borehole is inclined with a high inclination. The cuttings particle can settle on the low side if the conditions are not good, and therefore create a bed. And cuttings particle can be transported at the top of the bed because of erosion of this bed. They can return back to suspension if the conditions inside the borehole are changing. So cuttings transport is not a steady state phenomenon at all. It's really a dynamic one, where you have quite a lot of exchange for the position of the cuttings particles into a cross section, and you need to think about that it is changing for the whole length of the well. So I will try to illustrate that with the simulation that we do with our transient cuttings transport model. And you can see here for this particular well, which is, as you can see here from the wellbore architecture, a tapper architecture. It was necessary to have a very large hole size to put a submersible pump, because it's a very depleted reservoir and we need to have a submersible pump actually to lift up the fluid. And because of that, actually, the fluid velocity was very much reduced in this very large section of the hole. And because of that, there was a cuttings bed as calculated by our transient cuttings transport model, which settled there. And after many hours of circulation, that cuttings bed was relatively filled, and then cuttings managed to pass over the cuttings bed back to surface. Now, if we see here, when we are actually pumping and drilling and everything is okay, so those cuttings are being transported to the surface. There is a cuttings bed. Just afterward, so we are actually stopping the rotation because we do a friction test. And when the rotation is stopped, so of course there is lifting forces to lift up the cuttings particles which are on the low side. And therefore there is more cuttings particle which tends to settle on the low side. Nevertheless, most of the cuttings particles were estimated to be on the high side and therefore being able to be transported during the friction test. And then in the next part, so we do the connection and therefore we stop the flow rate. We of course have stopped already the rotation. And what happened is, because this well is very much inclined, we are close to, or we are at 90 degrees for most of the well. So basically most of the particles which were on the high side settled on the low side because the distance for them to fall down was very short. And as you can see, there is almost no particles which are left in suspension, except those which are close to the vertical section part. And most of the other particles are settled in the bed. Okay, what happens when we start the pump again? We start the pump, and we start the pump at the same level as it was before. And nevertheless, because when we have started the pump, almost no cuttings particles are going back into suspension. They are still left on the low side, because actually only circulating without having the support of the rotation of the pipe is not sufficient to return those cuttings particles up to the surface, to the high velocity field, which is on the high side of the cross section. It's only when we put the rotation again that actually those particles are lifted up from the low side and therefore being transported again. So you see that even though we are having the same conditions that when we were doing the friction test, the results on the transport of the cuttings are quite different because the sequence of operation is different. So it shows that actually this cutting transport is a non-nomic process. That means that it depends actually on the sequence of actions that has been applied to be able to estimate how it is working. Okay, cuttings particles also influence mechanics. And that's because basically when cuttings particles are cutting on the low side, they can be trapped below the tool joint, and the tool joint will grind those cuttings particles, and the cuttings particles getting out of the tool joint on the upper side will be smaller in size. Now this is absorbing some energy, the grinding energy to grind those particles, and this is transformed into an additional torque on the tool joint. And this torque actually is something which is measurable at the surface. Now, there is a side effect of this grinding process is that actually, even though the cuttings particles which are generated by the bit are more or less monodispersed, when you measure the cuttings particles when they arrive at the surface, they are very much polydispersed, and you get actually cuttings particles ranging from a few microns to several centimeters, depending whether they had the chance to travel on the high side up to the surface without being grinded at all, or if they have been very much grinding by many different tool joints during the process. Now, this additional torque, which is caused at the level of the tool joint, can actually cause very strange effects. And that's, for example, stick slips, which comes from the poor conditions for transporting cuttings. So if you say, for example, that you have a flow rate And that flow rate was sufficient, just barely sufficient to transport the cuttings, and the rotational speed is maintained constant. And you reduce slightly those flow rate. What can happen is actually those cuttings particles are getting more and more concentrated on the low side. They are generating more torque. And when they are generating more torque, they slow down actually the rotational speed. Because they will slow down the rotational speed, the cuttings get even more on the low side and they create even more torque. And that can induce stick slips of rotations just because of the change of flow rate. And you may think, okay, this is something which is simulated, but this is actually something that we have observed with high frequency measurements into actual drilling operations. So each time there was downlinking to the BHA, and there was a change of flow rates, actually there were a generation of extremely heavy stick slips. And when the downlinking was finished, actually, this stick slip was disappearing. Okay. Now, friction in wells is quite a difficult topic because it introduces a lot of non-linearity. So if you look at static friction when the two surfaces are not sliding compared to each other, basically the static friction is any forces which is in between a maximum in absolute value static friction force. But this friction is basically the friction which is necessary to make sure that actually there is no sliding between the two surfaces. So we solve that equation for any place along the drill string so that we calculate what is exact friction force, static friction force, so that there is no sliding between the two surfaces. Now, when there is sliding between the two surfaces, so we have kinetic friction. And basically in drilling, so the kinetic friction is essentially dominated by boundary friction, which means that it doesn't depend very much on the velocity between the two surfaces. Except that actually at very low velocity between the two surfaces, actually this friction is increasing, the friction force is increasing up to the static friction force limit. This is a typical Strebeck type effect. Now, the fact that actually the friction force is increasing when the velocity is decreasing is a source of negative damping, and that can be the cause of stick slip situations. So we can see here when we start the top drive that it takes actually time for the rotational speed to propagate down to the bottom of the bit. And when it has propagated to the bottom of the bit, so we get actually with this speed of 50 RPM, we get actually stick slip continuously. It's only when we increase the rotational speed of the top drive to something like 140 RPM that actually those stick slip disappear. And we have noticed that with many operations where we have high frequency measurements, that actually the use of very low top drive speed is a source of a lot of downhole stick slip, even off bottom, especially when you have a very tortuous well. So this is very well reproduced by this type of model, which is using this Strebeck and exact static friction calculations. Now, friction is also dependent of the direction of the sliding between the two surfaces. So if you have a velocity vector describing the direction of those sliding surfaces, so the friction force, the kinetic friction force, is always in the opposite direction of that one. So if you have, and that is a source of both the torque and the drag force. So that needs to be accounted for. But what is interesting is that the magnitude of the kinetic friction force is independent of the velocity, as I said earlier, because it's a boundary dominated by a boundary friction mechanism. So you can say that actually this kinetic friction force is a kind of vector which can move on a circle of a certain radius, and this radius is defined by the magnitude of the kinetic force. And therefore, you can have a propagation between rotational friction to axial friction relatively simply. And if you use that into linking the two set of equations for axial and torsional equations, then actually you can see things like what I will illustrate with this animation, which shows that when we are starting the rotation, when we are starting the block movement, an axial movement, actually we are inducing torsional oscillations into the drill string. So it's because of this effect that actually it is easy for the kinetic friction force to transfer between axial and torsional oscillations, so that we get this oscillation there. Now, the flow is also inducing forces along the drill string. You have a difference of pressures between the two sides of two joints due to pressure drops, pressure gradients into the annulus, but also inside the string. This creates forces. And if you have actually an axial movement of the drill string, so therefore you have swab and surge, those forces will change. And actually, this will have an impact on the stability of some of those torsional oscillations that I've mentioned there. So if we make a simulation of a rim up, rim down sequence, we can see that actually when we are rimming up, so lifting up the string and rotating, we see actually that torsional oscillations are damping quite fast. And the torsional oscillations that are initiated because of the change of the velocity vector that I mentioned earlier, because we have the actual movement combined to the rotational movement, is quickly attenuated because the swabbing forces, or swabbing pressure induced forces are actually positively damping the torsional oscillations. So they are attenuated faster than if we stop the actual movement and we have only pure rotational movement, and they are attenuating also because of another mechanism, which is due to the shear stress at the wall of the pipe, but they are attenuating faster. On the opposite direction, if we are rimming down, the surging pressure actually are a source of negative damping, and therefore these torsional oscillations are increasing in size. And actual measurements made in actual drilling wells shows that actually it can even go to full stick slip conditions when you are rimming down due to those pressure-induced forces due to swabbing, to surging. Altogether, so you have seen that we have actually 4 different types of models: heat transfer model, string hydraulic model, string mechanic model, material transport model. All of those 4 models are transient. They're all working together very tightly, and these together gives the full state of the system. And the full state of the system is pressure, temperature, density, fluid velocity, cuttings proportion in suspension, in bed, rheological behavior, side forces, tension, torque, rotational speed, axial velocity, elongation, and twisting along the string and the annulus. And these calculations are made by those 4 models at 100 Hertz. So every 10 milliseconds, you get a new picture like that, which is giving actually the description of what happens into the well. So the only condition that you have there is to get these inputs, and then you get the full description of the whole system at every 10 milliseconds. Now, of course, if we want to compare the result of those measurements, of those predictions with the actual system, so we need to compare measurements. And the problem with measurements is that actually they are never made exactly where we want to have them. So we need to have also models of the measurements of the sensors. And one of those models is one which is about the pit volume variations, as it's a source of information for gain and loss detection. And you can see here that we have also transient models for how the fluid is transferred from the well outlet to the pit by accumulation into the flow lines, the shell shakers, and so on and so forth. And we have actually a relatively good match between the pit volume variations compared to this delay which are introduced by these systems. on the pit volume. We have similar things about hook load measurements, depending of where you put your hook load sensor, whether it's at the deadline or the top of the top drive, and so on and so forth. Okay, so when we have model values, measurements, and measured measurements, we can start to try to utilize that to do practical work. And that's what we would like to do with this early detection of the deterioration of the drilling conditions. But things are more complicated than what I explained, and because we have to deal with uncertainty. And uncertainty is really a very important aspect for the type of work that we are doing. So you have uncertainty, of course, of the model, and that's accounted for, but you have also uncertainty of the inputs. And if you take usual information that you get from the rig side is, for example, you will get the mud weight, which is measured at one temperature, let's say at 50 degrees Celsius, and atmospheric pressure. And then you need to use that information to extrapolate what is the mass density of the fluid at different pressure and temperature, and also maybe at with different concentration of cuttings. And of course, depending on the level of details that you have put in the description of your fluid, you may get quite a lot of variations on the PVT behavior that you can extrapolate. So if you only know something about the density, but even don't know whether it's oil-based or water-based, or the constituents for the different components of the fluid, you may get actually quite a large uncertainty on your hydrostatic pressure at the deeper depths. If you know more information, you can reduce that uncertainty. But depending on the type of information that you get, you may get more or less impact on the uncertainty estimations. And uncertainty propagation in this context is quite complicated, and that's the kind of things that we try to do in our research. Uncertainty is also associated with the rheological behavior. Here in terms of, let's say, if you get the FAN 35 rheometer information, the maximum precision you can get from that is plus minus a quarter of a Pascal, if you are really lucky and have a good mud engineer. And because of that, actually, your rheological behavior is quite imperfect as it is captured by the FAN 35 rheometer. And you need to account for that for any pressure losses that you will do afterward, because this uncertainty will play a role on pressure gradients that you can calculate. And of course, you need to extrapolate that FAN 35 rheometer measurements, which has been made at 50 degrees Celsius atmospheric pressure, to different values of pressure and temperature, and also with a different composition, especially when you are transporting cuttings, as it is changing the apparent rheological behavior of the fluid. And when it is propagated, you can see how much your pressure gradient can change as a function both of the uncertainty that you have your rheological behavior, or the presence or not of cuttings into your fluid. And then you can utilize that the uncertainty propagation for estimating whether your model is predicting correctly or not what is observed. There are some uncertainties which are more like ill-defined information. I would just mention, for example, the average linear weight of the drill pipes. If you take the linear weight of the drill pipe and vary it by half a kilo per meter, this may give you a difference of 5 to 10 tons at the hook load. So you need to recalibrate that compared to the observation that you have. And this is what we do into an operation which we call global calibration loop, because we don't expect that the linear weight of the drill pipe are changing very much through the drilling operation. Of course, you have always certain wear on the pipe, but that should not be too much during one single operation. So we have actually these models that we have been discussed with the current state estimation, the current output estimation of the sensor, And then you feed that into a global calibration loop, which is actually filtering the information that is observed, picking up only the information which is relevant for doing this global calibration, and then feeding back that to the current state estimation that we get better estimation afterward. Now, some of those information which are ill-defined are changing through time, and that can be mechanical friction, hydraulic friction, and so forth, the bit aggressivity, and of course the formation strength. These are calculated or estimated on the fly during the drilling operation continuously by detecting the states which are actually relevant for calibrating those information. You see here the calibration of friction test for the hook load and the torque while we are doing this friction test, and we have a remnant torque which has been trapped into this deviated well. These are new imbricated loops which are calibrating those time variable parameters, ill-defined parameters, like the bit aggressivity, the formation strength, the hydraulic continuous friction, and mechanical friction. And these also, again, enter into the current state estimation, which are feedback into this. Now, when we've got that, so we get actually estimation of the state of the system, which is not only one single line, but it's actually a probability distribution of those different lines. And then we utilize those probability distribution for the state estimation of the system to detect whether there are changes in the downhole conditions. And there we can detect whether there are changes in the kinetic friction, for example, change in the annulus hydraulic friction, indicating that actually there are something happening, for example, with cuttings transport. Or we can also look at the fact that we have outliers in this animation, which is coming from an actual operation. Just notice what happens with this, the two toggles, the green toggles there shows the uncertainty which is accepted for the hook load, and you can see how sometimes the hook load is going far below these limits there, and that's actually automatically detected set-down weights. So the frequency of those set-down weights can, or these outliers, can be used actually as a source of information for detecting deterioration of downhole conditions. The same effect here for the pump pressure. So you can see here that the uncertainty that we estimate for the pump pressure, and you will see that the pump pressure suddenly just passed above the max uncertainty. So you see this alarm on high SPP. And if we look at the frequency of those things, we can see some micro pack-off situations, which are almost barely impossible to detect for a human being, but they can be detected by system. And this can be warning signs for a particular situation. And this particular situation is summed up with this animation there. That's one operation I was attending. And I looked at all those information that I mentioned earlier, and I could say 6 hours before the big incidents which will happen in a few moments, that actually there was very poor cuttings transport. The drilling team couldn't understand, could see that there was actually poor cuttings transport that did continue to run the operation, and then they came into this extremely large pack-off and the necessity to cure the problem, which took about 24 hours to get rid of the problem. But looking at those weak signals that I mentioned earlier, I was really capable of showing that actually there was poor cuttings transport, and they could have taken actions almost 6 hours earlier. Okay. So how can we use these type of dynamic models that I've described for automatic drilling assistance? Well, that can be used for example, the problem of detecting overpulls and set-down weights. Here is an example of an actual operation where we are pulling out a fall and everything is fine for one stand, and when we get to the next stand, so we get an overpull, we try to go down, we get a set-down weight. This is typically what Walt Aldred has qualified as a quick event detection. In the more general terms, that is referred as fault detection, isolation, and recovery. And this is a topic in cybernetics. And basically, we have been working on developing different type of FTIR solutions. And one of them is about overpull and set-down weights. No, overpulse and sediment waste is not simple things to detect, because it depends on many different type of context. Like, for example, what is the flow rate? What is the rotational speed? Is there any air gap into the string? And these are actually calculated by the system using those transient models that I mentioned earlier, in order to define what are the limits that should be respected. And of course, it changes with time because of depth which is changed, because of the temperature evolution, because of the load of cuttings. So these are actualized all the time, at any time during the drilling operation, and applied directly to the protection of the well, and reacting automatically when there is an incident. And I can just mention that just a couple of weeks ago, so there was an operation where this type of technology was used, and during one single day, this type of FTIR, that was a pump pressure protection, triggered 17 times during a day. And each of those times, they saved the well. So, and then they did manage to get out of the situation and continue to train as before. But human beings wouldn't have managed to react as quickly as possible to avoid those situations. And that happened 17 times in one single day. So this is what we can do about protection of the well by having this full detection, isolation, recovery mechanisms. They are part of this control loop, which is there, shifting directly the control of the three active elements of the rig: the mud pumps, the top drive, and the draw work. And they take control of that directly and apply automatic recovery procedures. These mechanisms are actually calculated based on this estimation that I mentioned earlier, the current state estimation with this global calibration and the local calibration. The other protection is about safe operating envelopes. The drilling system is very length-based. There is a lot of inertia, there is a lot of elasticity, which causes a lot of delays. And as you can see here through this animation, when we are pulling the string, and that's 20 times in speed, you can get actually a very long duration for swabbing periods. And you can see here the swabbing effects are just stabilizing about past 2/3 of the stand. Before that, actually, it's oscillating quite a lot, and it's very and that has to do with the acceleration that we have at the start and the dynamic of the drill string. And if you don't account for this dynamic aspect, actually, you will never be able to find what is the right speed that you can pull the string. As soon as you start to move the string, you will induce these effects, which will last for some time. So you need to protect ahead of time, and that's what we call safe operating envelopes. So safe operating envelopes for actual velocity and for depends on many different external conditions, like whether you have circulated or not, whether the fluid is gelled or not, so the duration for gelling period. It depends on the flow rate if you are pumping. It depends on the rotational speed. And it depends on the acceleration and so on and so forth. So there are many different contexts which are important actually to be able to calculate those safe operating envelope for the actual velocity. We do calculate all those safe operating envelopes, not only for the swab and surge case, but also for circulation in terms of maximum flow rate, which should be applied at any time. And this is combined with the set points which are given to the drilling control system, so that actually the safe values are passed to the drilling control system, even if the driller is asking for something which is unsafe for the well. And finally, so we can do when we have these protections by the fault detection isolation and with the safe operating envelopes, so we can do automatic procedures. And here is an example. That's a friction test. A friction test needs to lift up and slack off to record the pickup weight and the slack off weight. And you can notice here with this calculation that you have there that actually the length by which you need to slack off is much longer than the length that you need to pick up. So if you only base yourself on the observations that you've got there, you will always miss your friction test. You will not have enough length actually to do a proper slack off. So you need to do those calculations ahead of time. You need to account for the current conditions, both in terms of bit depths and heat conditions or temperature conditions and cuttings transport conditions and so forth. This is calculated on the fly all the time for any of those automated procedures. And those automated procedures are including friction test, reciprocation, pump startup, top drive startup, and so on and so forth. And this is the last level that you have there. And when you have all those protection mechanisms with the fault detection, isolation, recovery, safe operating envelope, and dynamic state automata, so then you can actually perform quite safe operations. And the results of these things is that actually this has been applied in North Sea for about 4 or 5 years, and the number of sidetracks has actually decreased after applying this type of methods from 30% of the wells to 10% of the well. So it has a very strong impact on the safety of the operation, and the performance has increased at the same time. Now, just a brief look at autonomous drilling. The classification from DSATs on drilling automation is a 10-level scale, where 1 is manual control and 10 is full automation. So we have a research project where we look at how to achieve full automation, completely autonomous system, where there is no human being involved. And if we want to achieve that, so we need to have a system which is flexible to changing environment and changing goals, a system which is learning from experience, and a system which is which can make appropriate decisions based on perceptual limited perception of the current state, and also final computations. So the way we address that is that actually, on one hand, we want to have the maximum performance, drill fast, shorten the weight-to-weight procedure, have less as possible extra functions which are not useful, and of course, have quick pipe ending during connections. But on the other hand, we want to balance that with the risk. So we have risk of vibration, we can have risk of back-off, hole collapse, formation fracturing, influx, washout, stuck pipes, and so on and so forth. And how do we balance this? Is by solving an optimization problem, which is a multi-objective optimization problem, where we have actually those two objectives, having the maximum performance and balance that with the risk. How do we manage that? So we have an objective function, which is the time to reach the section TD. And the time to reach the section TD is the time which is necessary to execute those operations which are coming to performance, and have the least possible amount of delays coming from curing problems associated with risk. So basically we have a continuous estimation of the drilling downhole conditions. Do we have root problems? Do we have stick slip? Do we have lateral vibration and so forth, buckling? And these estimation of drilling conditions are translated into risk levels. These risk levels are associated with estimation of possible delays, which can come with them. And then we have an automatic mechanisms to decide on what is the best sequence of actions to do to deal with this situation. Is it sufficient to lower the ROP because we have detected that we have poor cuttings transport, and to perform a friction test to get additional information about the downhole conditions? Or do we need to do a reciprocation to clean the hole even better? Or do we need really to stop drilling and circulate the hole clean and perform friction test? Each of those different sequences there will have different costs, because that will decrease the performance, but we can gain more information and we can stabilize better the situation. And we need to look at the overall aspect of the performance to reach the section TD. We will have a demonstration of that autonomous drilling system on our test rig here at in Stavanger at the beginning of 2021, where we will drill a well, and we will induce very poor downhole conditions. And we will see whether the autonomous system is capable of adapting to these very poor downhole conditions. So this is the overall schematic of the autonomous system with all the hierarchical control which are imbricated in the mechanism. So as conclusions, so we've seen that drilling systems are very mostly subjected to transient effects, and therefore transient models are really key for being able to understand what is happening. The internal state is a very complex problem with distributed information both in space and time, and we need to run at a very high speed. So all those models are running at, the whole evaluation of the internal state is done at 100 Hertz every 10 milliseconds, because things are happening very fast. And we are combining the effects of both heat transfer, material transport, drilling hydraulics, and drilling mechanics. Then we can utilize this information to propagate uncertainty, and this uncertainty is useful to estimate the weak signals to detect what is a deterioration of the downhole conditions. These weak signals are important to control what can be done in terms of detecting or to provide solutions or proactive actions for avoiding what's called non-productive time. And then we can apply that for fault detection, isolation, and recovery functions directly on the machine, safe operating envelopes, and combine that with state automata, which are dynamically reconfigured at any time to account for the actual down conditions. And then this is combined into an autonomous system that we are developing at the moment, and we will be testing within a few months. With this, thank you for your attention. And if you have any questions, so I will try to answer them.
Well, thank you very much, Eric. I really appreciate that. That was very comprehensive coverage of the drilling process and the work you're doing. So anybody, if you want to raise your hand, or you can unmute and ask a question.
Hello, Dr. Cayeux. Thank you very much for your presentation today. I really learned a lot. So may I ask if those real-time simulation tools are applied in the in the field that are currently using it, those companies?
Yep. Yeah. So this type of technology has been used for the drilling of I think 350 wells now. So we have statistical information about what is the impact of the use of those tools, because there start to be a substantial amount of background data. And it has actually had a large impact on improving performance and reducing delays. So they are used in the field, and there are 6 rigs which are installed with this drilling automation part, that the fault detection, isolation, and recovery, safe operating envelopes, and the reconfigured safe automata. 6 rigs, offshore rigs, with in-heave condition, which are using that every day. Yeah.
Thank you.
Other questions? Go ahead.
Yeah. So this is Chifan from UT Austin, and I have questions. So is the fault detection that you mentioned mostly for drill string side, or it also involves the detection on the well control events for the hydraulic side, such as kicks?
Yeah, we don't have kicks, no. We have pack-off situation, which is detected. So there is hydraulic side, but not the kick. And the reason why we try to solve the problem with the kick, but the problem with the kick is that there is no good sensor for measuring the flow rate out of the well. So we've been working on that as well to try to improve the measurement of the flow rate out of the well.
I see. Yeah. Thank you.
I was just going to add on to that question real quick, Eric. So you mentioned sensors. So is your limitation for application and success more the availability of the appropriate and accurate sensors, or is it the software and the physics?
Well, I would say first the sensors. We see that actually to install that type of software, you need to have actually proper measurements at the rig site. You need to have, we need to have information at 10 Hertz coming into the system. All those things we are talking are extremely fast. Imagine what it is actually in Norway when you have a rig which is operating with heave with 5 meter. You get seasick quite well, quite a lot. And the drill string is moving a lot also. So you have a very, very strong transient effects there. So you need to have access to the string control system with very high frequency, which is not so simple to get access to. And you need to have proper instrumentation. So you said it, measurement is the key. Yeah. And one aspect we have been very eager to get better information is about rheological behavior. And I know that UT Austin is working very much on that. So I would love that you succeed with this type of measurements, because I'd like to have them installed on the rig.
Great. Other questions? Okay, I think we'll wrap up our formal session here. And thank you again to Eric. We really appreciate the time, and hope to have you be able to come here and visit us in person someday. You know, I guess, I don't know if people from Norway, I think, can come to the United States, but we can't go to Norway right now. So I guess you'd have to come here. But I'll leave the session open for a while. I don't know if you have a little bit of time, Eric, there might be some students that would like to chat with you afterwards. And I would encourage you as a student, if you want to chat with Eric a little bit further informally, turn your video on so he can see you. And I'll just leave the session.